Welcome back to G Fun Facts Online. Today we are doing a deep dive into one of the most significant computational achievements of the 21st century. We are leaving the introduction short because we have a lot of ground to cover. We are talking about the first ever simulation of the Milky Way galaxy that resolves individual stars, not star clusters, not gas clouds representing stars, but 100 billion individual stars, simulated in real-time physics. This happened in late 2025, led by the RIKEN Center in Japan, and it fundamentally changes how we understand the universe. To understand why this is such a big deal, we have to talk about the billion-body barrier. For the last 50 years, astrophysicists have been stuck. The central problem of simulating a galaxy is that it is an n-body problem. You have n number of objects, which are stars, gas clouds, and dark matter, and every single one of them exerts a gravitational pull on every other one. If you have 100 billion stars, calculating the forces for just a single moment in time requires a number of operations so vast, it essentially defies comprehension. Because of this, for decades, scientists compromised. They used shortcuts. In famous simulations from the 2010s, like Illustris or Eagle, the particles you saw on the screen were not stars. They were massive tracer particles. Each dot represented a cluster of tens of thousands or even millions of solar masses. If you looked at a simulation of the Milky Way from 2020, you were looking at a low-resolution point list painting. You were seeing cities of stars blurred together into blobs. But gravity wasn't even the biggest problem. The true enemy of the galactic simulation was the supernova. A galaxy evolves over billions of years. To simulate it, you want to take large time steps, jumping forward 10,000 or 100,000 years at a time. However, inside that galaxy, individual stars are living fast and dying young. A massive star might explode in a supernova, which is a violent event that plays out over seconds and days. The shock wave heats the gas to millions of degrees. To simulate this accurately, the computer needs to slow down. It cannot jump 100,000 years. It must calculate what happens every few days to capture the physics of the explosion. This created a paradox. To simulate the whole galaxy, you need big time steps. To simulate the stars that drive the galaxy's evolution, you need tiny time steps. If you tried to simulate a whole galaxy with the tiny time steps needed for individual supernovae, the calculation would take longer than the age of the universe. In fact, the RIKEN team estimated that running a star-by-star simulation of the Milky Way using conventional methods would take 36 years of continuous runtime on the world's fastest supercomputers just to simulate 1 billion years of history. The door to the digital twin was locked. The breakthrough came not from a faster chip, but from artificial intelligence. The team, led by Keiichi Hiroshima, realized they didn't need to simulate every single second of a supernova explosion every time it happened. They just needed to know the result. They built what is known as a deep learning surrogate model. First, they ran traditional, extremely high-resolution simulations of just supernova explosions. They simulated thousands of these explosions in exquisite detail, creating a library of ground truth data. They taught the computer exactly how gas expands, heats, and pushes outward in the 100,000 years following a blast. Then, they trained a neural network on this data. The AI learned the physics. It learned that if a star of a certain mass explodes in a gas cloud of a certain density, the resulting bubble of hot gas will look a specific way. Once the AI was trained, they plugged it into the massive galactic simulation. Now, when a star in the digital Milky Way reached the end of its life, the supercomputer didn't grind to a halt. It simply asked the AI what happens next. The AI, recalling its training, instantly predicted the expansion of the gas. The result was a computational miracle. The old method took 315 hours to simulate just 1 million years of galactic time. The new AI method took 2.78 hours. That is a speed up of over 100 times. Suddenly, the 36-year runtime shrank to just 115 days. This allowed the team to deploy the simulation on Fugaku, the crown jewel of Japanese high-performance computing. They utilized approximately 7 million CPU cores. To put that in perspective, a high-end laptop has maybe 14 cores. This was the power of 500,000 laptops working in perfect synchronization. When the simulation began, it didn't just spawn a static picture. It started with clouds of gas and dark matter, and let gravity take the wheel. Researchers watched as the gas collapsed and fragmented into individual points of light. 1, 2, 1,000, a billion. The screen filled with the dust of creation. The digital twin was born, possessing spiral arms, a central bar, and a dense bulge. But if you zoomed in, you would see individual stars. You could track a single star as it drifted through a gas cloud, got kicked by gravity, and eventually exploded, triggering the AI surrogate to blow a bubble in the virtual gas. So why does this matter? Is this just a flex of computing power? No. This unlocks new science that was previously impossible. The first major implication is chemical tagging. Every star is a time capsule. It preserves the chemical composition of the gas cloud from which it was born. In the early universe, there were only hydrogen and helium. Heavier elements like carbon, oxygen, and iron were forged in stars and sprayed out by supernovae. In old simulations, this mixing was averaged out. You knew a region had more iron, but not which stars carried it. In the Galactic digital twin, researchers can track the chemical history of specific stars. They can see how a single supernova enriches a nearby cloud, which then collapses to form a second generation of stars with a specific ratio of oxygen to iron. This allows scientists to compare the simulation directly with data from the Gaia Space Telescope, which is currently mapping the chemical composition of millions of real stars. If the simulation matches the observation, it validates our theories of how the elements of life spread through the galaxy. The second major implication involves dark matter. Dark matter makes up 85% of the matter in the universe, but it is invisible. Theories predict it should be clumpy, forming thousands of tiny subhalos swarming around the Milky Way. But we don't see thousands of dwarf galaxies. We see only a few dozen. This is called the missing satellites problem. A star-by-star simulation offers a new way to find these invisible clumps. As a dark matter subhalo passes through a stream of stars, its gravity should disturb their orbits, creating a wake or a gap in the stream. These disturbances are too small to be seen in low-resolution simulations, but with 100 billion stars, these delicate streams are visible. Researchers can now use the digital twin to predict exactly what these scars look like. They can tell observers to look at a specific stream of stars, and if they see a gap of a certain size, it is proof of a dark matter subhalo. This turns the digital twin into a treasure map for hunting dark matter. The third implication is the formation of globular clusters. These are ancient, dense balls of stars that orbit the galactic center. Previous simulations couldn't resolve their internal structure. They were just dots. The RIKEN simulation resolves the stars inside these clusters, showing how they interact, share energy, and sometimes get ejected. This could finally settle the debate on where these ancient fossils of the universe came from. Beyond astronomy, the impact of this technology extends to Earth. The technique used here, using AI surrogates to replace expensive small-scale physics in a massive system, is the missing link for climate change modeling. A global climate model is like a galaxy simulation. You have a massive system, the atmosphere, driven by tiny events, like cloud formation and raindrop physics. Just as we couldn't simulate individual supernovae, climate scientists struggle to simulate individual clouds in a global model. The RIKEN team has stated that their AI surrogate method is transferable. Climate scientists can train an AI on high-resolution simulations of cloud physics and plug it into a global climate model. This could lead to the first cloud-resolving digital twin of the Earth. vastly improving our ability to predict extreme weather and the long-term effects of global warming. We are entering the era of brute force precision. For as long as computers have existed, science has been the art of approximation. We approximated cows as spheres and galaxies as fluids. The 100 billion star simulation signals the end of that era. We are no longer limited to modeling the average behavior of a system. We can model the outliers, the rogues, and the anomalies. In a system of 100 billion, it is often the 1 in a billion event that changes everything. This breakthrough also brings us philosophically closer to the simulation hypothesis. If we can compress the physics of a supernova into a neural network and run a galaxy on a silicon chip, it forces us to wonder about the nature of our own reality. But for now, the researchers at RIKEN are content with their virtual galaxy. They have handed humanity a new map. It is not a paper map of static lines, but a living, breathing, evolving model of our cosmic home. We have built a mirror for the Milky Way, and for the first time, when we look into it, we can see every single star looking back. That is the story of the Galactic Digital Twin. Thank you for listening to Fun Facts Online.